All right. Well, thanks again, and hello again. It's me again. So last time I started discussing the various models or the various families of models that one can typically be interested in statistical mechanics. And I gave you a little exercise, which I think is fairly illustrative of key questions and methods that people ask and implement in statistical mechanics. So I just to conclude the discussion of last time, the point that I was trying to make is that if you have long-range attracting interactions, or attractive interaction, or attractive interactions, then there's a risk of close packing. Okay, and the way I suggested to treat this problem mathematically was to describe the first situation that would correspond to normal situations where particles are fairly well spread out, and then a second situation describing a subset of phase space that corresponds to particles being closely packed and occupying only a portion of the total volume that they are given, and then computing in both cases the typical energy, and then computing the volume, and showing that and observing that one situation was preferable for energy, one situation was preferable for volume, but if you take into account the sum of both, there's one situation that wins, and in that case, it's the closely packed situation. So what did we need to do in order to understand which situation would be preferred by the ensemble, by the probability measure, so by the physics, if you want? We needed to so for this comparison, we needed to evaluate the energy of, if you want, the typical energy of a situation, and then the volume in phase space, and then combine both, because what appears in the exponent, it's something like this, and you want to minimize or what I want to say, instead of minimizing, it's like which situation is that minimal, is that smaller. Okay, and the situation for which this is the smallest is the winning situation. And what are the sort of the moral of this thing is that computations of energy and volume are key. You can't just base your intuition on one and the other, right? And of course, these sort of computations, they come with a simple difficulty, which is I need to describe this situation in a precise mathematical terms. It seems silly to say it, but it's actually hard, because if I say, oh, typically closely packed situations, closely packed configurations will be preferred. Well, you have every right to ask me, what precisely do you mean by closely packed situation? When is it closely packed? When is it not closely packed? Can you write a formal definition of the subset of all configurations that you're calling closely packed. And what do you mean by regular configuration? And I try to give a sense of what an answer could be. But if you move to more realistic or more interesting situations where you say, okay, I want to prove that the system is a liquid or it's a solid. Okay, well, what is a liquid exactly? What exactly do you mean by a liquid? Which are the configurations in phase space that correspond to being a liquid or a solid? And well, these are not easy. It's not easy to give precise definitions of that. So you need to describe the situations precisely, and that's sometimes problematic. And of course, even if I describe these two situations precisely, and then I do the computations that I suggested in a completely rigorous way, and I observe that the situation with closely packed particles is preferable, it only tells me that between these two situations, there is one that wins. But it doesn't tell me that that's the situation that occurs, because there could be other situations that are not captured by my two options, and that have even better exponents, so even more mass for the probability measure. So there's a question of excluding other possibilities. And one mathematical tool to sort of make sure that we haven't missed another situation that would be even better would be to write or derive or obtain something that's called a large deviation principle, which basically consists if you in one word, in that context, it would be it would be if we manage to do or to write a formula or an expression for such a quantity or such quantities, minus log volume, which is called the free energy, and then argue that a typical situation for the canonical measure is equivalent to a minimizer of free energy. And if you do that, and then you manage to compute the minimizer of the free energy, so that's the last step, find minimizers of free energy. So in a large deviation principle for these questions of statistical physics would typically require to give some kind of explicit expression for this, and then prove rigorously that this is really the quantity that determines whether you're a typical situation or not, and then find among all phase space the situations that have the best free energy, and that this will be the answer. For more concrete examples, I would recommend, so there's this book that I mentioned by Rasulaga and Sepalainen, in large deviation theory and introduction to Gibbs measures, and they do by hand lots of examples. You can find a PDF online. It's not too difficult. Okay. So that was, but anyway, so the point I was trying to make at the beginning was to illustrate what could go wrong in the case of long-range interactions, but that's one, this is an interesting point by itself. But in the course of the explanation, we've also seen some of the computations and the questions that one could ask. And these sort of questions are obviously not specific to the catastrophe of having long-range interactions. It's a set of questions and methods that are used all the time. Okay, I won't maybe discuss, or maybe just briefly, because someone asked a question last time, and it's related to the question that was asked. So there is a problem that can occur if you are too attractive at infinity. So that's what I've just described. There's another problem that could happen, and it's even worse if you're too attractive at 0. So that's called the ultraviolet catastrophe, and that's strong. That's related to very strong attraction near 0. So if you think of two charged particles, but there's a plus and there's a minus, they attract each other, okay, and the interaction is in dimension 3 is 1/r. So actually it's minus 1/r. Okay, so here if you have two particles at 0, is two particles that are super close, the energy is minus infinity. At minus infinity, it's a fairly low energy. Okay, so if they don't have any hardcore, if there is no hardcore condition that prevents them from being too close to each other, what they want to do, energy-wise, they just want to collapse into another and just form one doublet. Okay. What could prevent them to do that? Well, what could prevent them to do that is the volume term, because two particles that occupy exactly the same position, this has 0 Lebesgue measure. Okay, so this is forbidden by the volume contribution. So then the question becomes, okay, is there a risk that is the volume contribution strong enough to forbid them to go very close to each other, or do they like each other so much that they don't really care about the volume and they will still be maybe not exactly at the same spot but very close to each other? So that's another energy entropy competition that one can compute. And in fact, so this corresponds to a non-stable interaction in the sense of stability that I discussed last time. And in fact, the partition function, that's the question that was asked last time or 2 lectures ago, maybe. In that case, the partition function might be ill-defined. So actually, this is a fairly well-known model, so I can expand on it just a tiny bit. If you try to do electrostatics in dimension 3 with just 1 plus and 1 minus charge in a box, this is ill-defined because the partition function, it's the integral over x, which is the position of the first one, and y, position of the second one, e of minus beta 1 over x minus y dx dy. And this you can compute is plus infinity for all beta, because the exponential thing, sorry, there's it's minus beta minus, so there's a plus. So it's e beta, and that explodes all the time. So in order to define electrostatics in dimension 3, you either need to have a hardcore condition, so saying that the atoms, they cannot, or the particles can't be too close from each other for some other reason, okay? Or you need to do a quantum description or something. What might be fun to observe is that if you're, for some reason, interested in doing electrostatics in dimension 2, in the same context, a plus charge and a minus charge, in dimension 2, the Coulomb potential, so what would be the electrostatic potential if we were living in a world of 2 dimensions? Here, the interaction is logarithmic. And the partition function becomes E of minus beta. So, and then now it's a plus because they like each other. Sorry, plus log R. And so it's really just one of, if you change coordinates and so on, you'll see that this is defined beta large enough. I think it's larger than 2. Maybe strictly, and plus infinity otherwise. So here's an example of a system that's well defined only at large enough temperatures. So sorry, at I'm sorry, it's the other one. It's small enough. Because you don't want to have 1 over R to a big power. Sorry. So but what the sentence that I said is correct. It's large enough temperature, and since beta is 1 over the temperature, it's small enough beta. Okay, so this is a system where you can make sense of the system only at high enough temperature, which physically corresponds to the fact that the particles have enough agitation that they don't really want to come too close to each other. They prefer to move around in the burst. Okay. Okay, so that's it. And maybe I can take just 5 minutes to list some classical models. Okay. Which you may have heard of some of them. Oh, before I go into that, it just occurred to me the discussion that we've just had about long-range potentials giving rise to typical configurations that are closely packed if the potential is attractive. And if the potential is repulsive and long-range, what will happen is that the particles will stick to the boundary of the box, right? So in one case, they stick to each other, and that's attractive potential. If the potential is long-range but repulsive, they try to fly away from each other, and they will stick to the border. Okay, I guess that's the situation already appears if you're looking at energy minimizers, and I think Dima discussed that in his lectures at the beginning, maybe the first or the second lectures, right? If you have these risk potentials and you change the S parameter, you see something pretty different on the torus or on the sphere. The picture is different. In some cases, the energy minimizers, they occupy the entire sphere, the entire space, and in some cases they concentrate around a certain region. Okay, so what might be interesting to observe is that this phenomenon is not only a zero temperature phenomenon, which corresponds to energy minimizers, but it's also seen with temperature when you do statistical mixing. Okay, so maybe just a quick list so if you're interested, you can see the names of these models, and so the most celebrated model is the Ising model. That's a lattice system. So the particles, they have to be on a certain lattice. Typically, it's Z to the D. It doesn't have to be this way. And they come with a mark, which here is called a spin, and the spin space is +1, -1. Okay, and then they have a certain energy, which is usually written this way. I guess it really depends on the notation is not standard, right? So that's the spin at position I, J. So that's in the lattice, the sum over all the lattice. And this is the, or maybe I shouldn't write I minus J. So it is a strength of interaction. Okay, and in the classical model, J of J is a constant times the indicator of A, J are neighbors on the lattice. Okay, but it doesn't have to be this. You can consider Ising models where all the spins interact with each other depending on, say, the distance between the sides. And it can be whatever distance you want. It can be the graph distance, it can be the Euclidean distance, it can be okay, and the dependency on the distance can be whatever you want. And I'm not just saying that, well, sure, it can be whatever you want, it's a free country, right? It's that people do study such variations on the Ising models, and they find that the physics varies. So you can also take a G to be a short range or long range, or so it can be the classical situation is its nearest neighbor, but it can be short range, long range. It can be mean field, which means that everyone interacts with everyone with the same strength. So typically you work in a big box, so you have a finite system, and everyone interacts with everyone with the same strength. And that's actually and in that case, if you do that, in that case, the energy only depends on the mean spin, so the average value of SI, and that's the origin of the name mean field interaction, because in that case, the energy depends on the mean field. And you can take dimension 1, 2, 3, 4 higher. This has been studied. So all these variations lead to interesting discussions. Okay, and my point. So I guess many of you have heard of Ising. It's a classical example. So I would suspect that many of you have met the Ising model in a talk or in a class or in your work before. Maybe what's interesting to know is that this is Ising is part of a larger family of models, which are called big O of n. So Ising is O of 1, and O of n means that the spins belong to the sphere of dimension n-1. So O of 1, the spins are just ±1. O of 2, the spins are on a circle, and that's sometimes called the rotator model. And this has been studied a lot. There is O of 3, where the spin is on the sphere, the usual sphere, and that's called the Heisenberg model, etc. Okay, so so there's Ising, and Ising is actually part of a larger family. And there are since these are lattice systems, they are in a sense, not that they are simple to study at all, but the fact that they are on a lattice, it simplifies some of the questions one could ask. And so for these systems, there are actual deep results about like there are answers to questions, let's say, which is more rarely the case for non-lattice systems. And maybe we'll mention some of the questions and answers later or tomorrow. Okay. So that's in the world of lattice systems. These are the dominant ones. Of course, there are other, there are other lattice systems, and there are more exotic ones, if you want, where the interaction is more exotic, or you could also see percolation theory as an example. And then there are continuous models. So in continuous models, you're just working in RD or in a box of RD, and then you have to specify the interaction. So I guess one example would be these systems where the interaction is RIS. So 1 over x to some power s. Okay. If s equals d minus 2, it's called Coulomb. If s goes to plus infinity, this is more like, sometimes people say that it's a limit of our sphere. I won't elaborate on that. A physically relevant example is the Lennard-Jones potential, which is something like that. So you have a repulsion and an attraction, and they don't play at the same scale. Okay, and so there are many other examples, I guess. Okay, so that concludes the example part, and I can move to something that maybe is deeper and more interesting, but it's good to have some names around and some examples around or in your mind. So I want to move to a completely different section, which has to do with the infinite volume limit. Okay, and so my goal in this section is to raise awareness about problems that occur when you're trying to give a mathematical treatment of what is called the thermodynamic limit. And thermodynamic limit, in the physical sense, it just means sending n to plus infinity, where n is the number of particles, or the number of spins, or the number of whatever. So in order to give sense rigorously to the mathematical, to the thermodynamic limit, we need a proper formalism. And then there are many technical problems and so on. And you could ask, okay, why bother? Like, why do we need to consider this limit anyway? The physics is finite. You have a finite number of particles in the room, right? So what sense does that make? Well, first of all, n, the actual number of particles, is indeed finite, but it's extremely large. So it's not completely crazy to consider the large n limit. Okay, but more than that, the real problem is that one wants to give a mathematical framework for studying phase transitions, which will be the topic of tomorrow's lecture, I guess, or at least partly. And there are no phase transitions for finite n. It's it's impossible in a sense to see anything that could be defined as a phase transition if you have a finite number of particles. Why? Because we'll discuss that, but the typical way of defining a phase transition is to say that some quantity is not smooth at some value of, say, the temperature. But if you work at finite n, almost every quantity that you can write down is a polynomial in all the spins and positions and temperature and so on. And so this is never singular, it's always smooth. Of course, it's going to be less and less smooth, or it can be less and less smooth as n goes to infinity, because you can approximate any bizarre function with a polynomial, but at finite n, there's nothing to be seen formally. So that's why people work in the infinite volume. Okay, so it's the only way to talk precisely about phase transition. And also, of course, it's pleasant, mathematically speaking, to study limits and construct infinite volume, the limiting objects, and study the limiting objects and so on. But there's also just a physical motivation that's pretty basic. Okay, so as I said, the thermodynamic limit, the general sense is sending n to plus infinity, but in papers in the physics literature, or in the mathematical physics literature, it has a more precise meaning. So usually it means something more specific. It means, so what I should say is proving existence of the thermodynamic limit means proving that the following thing exists, that the limit of so this will be the partition function with n particles. Okay, so what we assume is that for each n, we have, say, a box of size n particles, and then a certain interaction hn. Okay, so this gives rise to the canonical ensemble Pn, and then there's beta, the temperature. Okay, and there's also the partition function, which is the normalizing constant. Okay, and that's the n beta. Okay, and then once you've defined that object, you're asking whether this limit exists. Okay, so if you read papers and they say we prove existence of the thermodynamic limit, it means that they prove that this limit exists. And that is, in physical terms, that is the mean free energy. And you could ask, okay, well, how do we prove such a thing? And this is actually pretty cute, I think, because the main tool to prove so existence of the thermodynamic limit is a sub or superadditivity plus what is called Feket's lemma, which I assume all of you have encountered at some point, right? Is the idea is that if you have say a sub additive sequence, then this converges, and actually it converges to the inf of an. But the first point, there is a limit, and then actually you can characterize the limits. But even just proving the limits is interesting. Okay, and this kind of argument of sub or superadditivity is the main, if not the one tool that is used to prove existence of thermodynamic limits. Yeah, ideally what happens is that if you take a big system that is made of two subsystems, then you may hope that for some reason, if you have n and m particles in each box, that z n plus m is almost a product, because you can imagine that in the big integral, maybe for some reason you can separate variables. And then if you take the log, obviously this is going to give you almost additivity of the log of the partition function, and that will allow you to prove that log zn over n converges. Okay, and why should that be true? Well, for example, if the interaction is short range, then it's sort of the same argument as what I've done, or what I sketched last time when I did that, right? There was almost subadditivity of the energy. And so if you plug that in the definition of the partition function, you can assume, you can hope to prove some kind of almost additivity of the log partition function. Okay, so that's one thing. There are, of course, variations on Feketti's lemma. You don't need to have exact subadditivity. You can allow for error terms, and then it still allows you to prove some kind of convergence. So if you're curious, you can try to prove this, say for Ising in dimension 1. So in Ising in dimension 1, the setup would be the following. Say you have n plus m sides, okay, and on each side you can have a +1 or a -1 spin, okay, and the integral will be on the 2 to the n plus m possibilities of having plus or -1 at each side. That's the partition function. And then the energy is the energy that I wrote down earlier. So the energy is the sum over A. So here, if you do nearest neighbor Ising, you're just interacting with the guy in front of you and the guy after you. So it's going to be SI plus 1, something like that. Okay. And you can put that into the integral and try to say, okay, if I cut the box in two, if I cut the interval into, say, here, and I have n particles here and m particles here, well, the only contribution of one side with the other side is only right at the boundary, because sides only interact with their neighbors. So there's only one term where there is the guy at the end of the first block that interacts with the guy at the beginning of the second block. Okay, and this interaction is spin times spin, and that's either +1 or -1. That's big O of 1. Okay, so the energy is additive up to an error that is bounded. Okay, so if you put that into the expression of the partition function, you will see that you have almost additivity of the log of the partition function, and that allows you to give to prove the existence of the thermodynamic limits. As a caveat, I should say that in that specific model, we have an exact expression for the partition function. Okay, it's completely explicit. It's not obvious to compute it, but it's explicit. So, and you can compute its limit simply by looking at its expression. But you can also just prove the existence of a limit without having the exact expression using this kind of arguments. One thing I wanted to add around this topic is so that's for Ising nearest neighbor. I mean, I leave it as an exercise, but to check that reasoning is correct, you could do Ising with short-range interactions with the same argument, basically. So even if you're interacting with everyone else, but with an interaction that decays fast enough that the total contribution of you with everyone else is bounded, then the same argument works. Okay. And then for long range, well, it might not work. But it might also work in some cases. Okay. And in particular, it was I just mentioned it. It's a series of work that I happen to know a bit, and but there's a very cute argument. If you don't know the argument, it's I recommend looking at it, and it can also serve as an exam for your students. So these papers deal with Coulomb systems. Coulomb systems are long range. Okay, but they are also very fundamental because electrostatics and gravitational matter, for those systems, the interaction potential is Coulomb. Okay, so there are papers by Lieb, Narnhofer, and I forgot actually. I guess there's also Lieb, Leibowitz. You can read that in the book of Lieb, Sayringer, chapter. I think there's only one book by Lieb and Sayringer, chapter 14. And they use what is called the Cheese theorem, which is really a very clever subadditivity argument for Coulomb interactions. I mean, it has nothing to do with Coulomb or with statistical mechanics. It's a purely geometric construction that is used in that context. Okay. Like it allows you to do that. It allows you to do subadditivity. And here, it's long range. The key here is that it's long range, but the system is neutral. So there are cancellations due to various charges being present. So I think that's the answer that I gave yesterday to someone's questions. Even if the interaction is long range, the statistical mechanics is not doomed to fail, because maybe the interaction is long range, but if you have both attractions and repulsions within the system, the terms might cancel out and you still get something that's tractable in the end. And that's what happens with electrostatics in real matter. You have electrons and you have protons, and they give the interactions due to both charges sort of cancel out. Okay, and since I'm almost out of time, maybe I won't start a new paragraph. One thing I can comment on is just a caveat again. So I told you some people are happy with proving the existence of the limit. So what I want to insist on is that this is a numerical value. Okay, so this, if it exists, well, it exists, it's some numerical value, which is usually denoted as something like f of beta, because obviously it depends on beta. Okay, and so it's the mean, as I said, it's the mean free energy. Okay, and in the next and last lectures, I will try to tell you that the regularity properties of this are, for physicists, very relevant. But as mathematicians, we are also interested in not only the numerical value of some limiting quantity, but we could also ask, okay, the measure itself, T and beta, does it have some kind of limit? Okay, and that's a fairly different question, which is also relevant for physicists, I should say. Okay, and which requires obviously much finer arguments, or which at least sounds much more difficult than just proving the existence of a numerical value for a limit. Here you're trying to construct the limit of a more complex object, and we'll see next time possible ways of giving a sense to this sort of infinite volume objects and symbols and okay, so maybe I stop here and I will have enough for tomorrow, I think.